Okay, now we are into kinematics, which is revision 2 in your notes. We're going to today just look at kinematics and graphs mainly, but I will relate this to work energy and power as an alternative to describe and predict motion, which is the main branch of kinematics. So at first, you need to know the definitions of these things like displacement, velocity, and acceleration. The correct definition, don't write the equation. The equation alone is not good enough. Okay, and also work done and mechanical energy. So displacement symbol S. So V, velocity, is defined as rate of change of displacement, just like A, written in dv dt, is defined as the rate of change of velocity. So rate of change is what we're looking for whenever we talk about defining these physical quantities. Okay, so displacement is basically how far you move, velocity is how fast you move that far, and acceleration is your speed changing. Okay, so we're gonna use this definition to show you some graphs right now. Okay, and then we'll go back and talk about energy in another video. So when it comes to graphing an equation, we can graph displacement, which is your final position versus your initial position. And we can also graph velocity because gradient of displacement will give you velocity. If you are good in maths, and I assume both S3 and D should be fairly good in maths, right? Right? You did choose the course. So anyway, gradient here defined as ds dt is equal to v, and gradient for A defined as dv dt is equal to A. So whenever you go from S to V to A, you are seeking out gradient. When you reverse, you are looking for area. Integration ma. So area of V will give you S. I want to talk a bit about the sign here because there's a lot of common misconception about the signs. So for S itself, it's pretty straightforward. If you are towards the left, your S would be negative. Towards the right, your S would be positive. This is the general norm. You want to flip it also can, as long as it's consistent inside your question. Okay, so V will tell you which direction the object is moving, not the position, but direction. So your V can be positive with S positive, your V can be positive with S negative. Okay, so just like here, your S is positive, but your V is negative. I am on the right, but moving towards left. On the right, S positive, moving towards left, V negative. Okay, so there's no such thing where the signs are dependent on each other. It's not read or visualize the question. Okay, V here is related to the direction of motion. Okay, and acceleration. The best way to visualize acceleration is think about it as the direction of net force, because F equal ma ma. So let's consider a ball moving to the right. The V is positive, and I pull towards the right. The F is positive. So because the F is towards the right, you will also accelerate towards the right. So I can probably safely assume that ball 1 is moving faster, V increases. Okay, let's say case number 2, V is negative, but I still pull in the same direction. So as you can see, it's pretty like instinctual to tell you that ball 2 will travel slower or your V will decrease. Okay, I'm going to go away for a while so you can see the graph. Now, if you look at the graph that I'm drawing, V against T, you will notice that they both, because it's the same force is positive. So normally people would draw like this, no? V increase, V decrease, 1 and 2. Is that correct? Think about it first. Now, before I move on to ball 3. Now, ball 3, your force is negative, but your V is in the positive direction. So in this case, obviously, you are slowing down as well. Okay. So your ball 3 is traveling slower. Okay, and I think probably some of you would notice that at this point, there is a slight mistake. For graph 2, they have the same force, so they should have parallel acceleration. Same acceleration. Both lines have to have the same gradient. Okay, so let's go back to this ball number 3. Force and velocity opposite direction, the ball will slow down. If V negative and F is negative, ball 4 will travel faster. V will increase. Okay? So there's no such thing as positive acceleration must be faster and faster. Negative acceleration must be slower and slower. Okay? You need to talk about the actual direction. So when I say V decrease, I mean the magnitude of V decrease. So number 2 is still a decreasing V because it's moving closer to 0. Just like number 3 was positive and is getting smaller and smaller to 0, whereas number 4 is negative and becoming a larger negative. That's why number 4 is traveling faster and faster. All these lines have the same gradient because they have the same force, F equal ma. Okay, now sometimes, right, especially in the objective, they will have a graph against position. So this kind of thing, right, I would generally advise you use equations. Okay, I will do an example for you later, but you really need to try more questions. Okay, use some equations and common sense. You got one. Your teacher just never teach you how to use it last time. So now let's talk about the equations that I'm mentioning. So I like to call this the Stova equation. And normally it's derived from the VT graph. So I think you can find this derivation in usual textbooks. But this one is area of the graph. This one is from gradient of the graph. And you notice that each equation there's a term missing. So the last two equation is done by simultaneous equation of the first two equations. So the first equation has, I've forgotten to write, but the first equation has no A, second equation has no S, third equation has no V, fourth equation has no T. So step 1, you will list your variables, okay, to allow you to choose the equation. Like I will use the first equation if I don't have A, or I don't need to calculate A. Use the second one if I don't have S, etc., etc. Step 2, you should always choose the initial position of where your object is. And whenever you fill in, please remember to consider whether it's positive or negative because S, U, V, A are all vectors. And you can only use this 4 equation if the acceleration is constant. If it's not constant or your force is not constant, then cannot. So there are a few popular case studies that I will go through throughout the series of videos in revision 2. Mainly now we are going to look at free fall and projectile. Projectile is just free fall with a horizontal component. Okay, but before I try the question, I'm just going to define work done first. Work done is a product of force and displacement in direction of that force. And mechanical energy here, okay, by the way, work done is used to change mechanical energy from one form to another. So I'm just going to list down the equations. KE is half mv square, PE is mgh. And your elastic potential energy, if there's a spring or a rubber band, if let's say it obeys Hooke's law, then it's half kx squared, provided it obeys Hooke's law. And also finally, there's power, forgotten to type, rate of work done, dw dt. Okay. FV is sometimes useful, but I just didn't do it here because I wanted to make the video a bit shorter. We shall see. Okay, so as mentioned before, both free fall, which is linear, you throw something up and then you send it down. Oh wait, I can come back. You throw something up and then you send it down. It's one straight line. Okay, so this kind of linear, I have to draw a bit out, if not you can't label, you see. So let's say you project or you throw the ball up vertically at 90 degrees. And what will happen here is that, let's say it will hit the floor at the same speed. And at the highest position, the speed will be 0. Okay, and as it goes up, it's slower and slower. As it comes down, it's traveling faster and faster. Go throw an object and look at it. Okay, so if let's say we add a horizontal component to it, meaning instead of just throwing vertically, I'm going to throw it horizontally. Okay, this is actually projectile. And because projectile is new, it's kind of like a favorite question. You should expect some projectile question either in objective or some structure. So let's say I throw the ball at an angle theta from the ground. Okay, there's no new equation. The 4 kinematics equation, your Stuva equation should be enough. Anyway, if I throw it on the ground, it's going to travel in a parabola. If we have a lot of time, I will prove to you that it's a parabola, but we don't have this time, so accept it lah. Or find the proof yourself if you have time. Okay, so the ball is a bit like that linear motion, but you stretch it out horizontally. Okay, I'm not sure if you can see it. Just stretch out. Pattern now after MCO. Okay, anyway, let's say you project it at the angle theta from the horizontal and the initial speed u. And I'm going to resolve this to horizontal and vertical. Because these are vectors, I cannot simply plus or minus them if they are not on the parallel plane. Okay, so we do this thing that we learned in the previous chapter, whereby we resolve or split the vector u into just horizontal and just vertical. Okay, so I'm just going to put the ball at a several position like this so that we can label the vectors so that we have a better understanding, right? And I am going to draw, and you can see that the speed is a tangent to the curve, and then you can see that the angle keeps changing. It's just that by the time it hits the ground, it should have the same angle theta. But if you check the horizontal component is always the same, never change. Why? Because there is no force pushing or pulling unless you have air resistance. We assume there's none. There's no force pushing or pulling the ball left or right. So always it will be u cos theta. No horizontal forces, so no horizontal acceleration. And if you look at the vertical one, a bit hard to do but it is actually slowing down, which kind of makes sense because gravity is pulling it down. So at first it will be slower and slower because gravity and speed is opposite direction. And then after the maximum point, it will go faster and faster because gravity is traveling in the same direction. So at the highest point, vertical is 0. Because you see, we talk about u sine theta. And the angle is 0 because it's flat. So it's 0 0. Okay, so horizontally is always u cos theta. Vertically becomes smaller. So there is kind of like, you can see it's the same for linear. Highest position, vertical is 0. Horizontal is not 0. Now, because horizontal is not 0, Ke at the highest point is not 0, it's maximum. I'm going to label a few parts. How far the ball can travel horizontally is normally called the range. Time of flight is the time of the ball in the air, and you can have maximum height. They can ask you to calculate all this, derive an equation for you to calculate all this. Not needed, not really. So the Ke is minimum at the highest point, but not 0. You can always use your 4 equations of motions. Okay, so today we're going to focus on an example involving both of this, and also draw some graph. So normally I'll list down the Stuva. Let's say I want to find the maximum height. So I've chose the initial position as the ground and the final position as the highest point. So let's say we go upwards as H max because the ball is upwards from the original position. Then your acceleration is downwards. So A and S should have the opposite sign. The ball is traveling upwards, but the gravity is going downwards. So opposite direction, opposite sign. So if we do the STUVA for the X component and the Y component for your projectile here, the first thing you can fill in is acceleration. It's always the same. Okay, and you notice that the Y component is the same as, again, the neighbor on the right. The only difference is the speed. Because you resolve already, one will be u cos theta, one will be u sine theta. And the Y component, when you reach H max, you are half the range, and the time is always the same because the ball is at the same place at the same time. You only got one ball, not 2 balls. It cannot be at 2 different places at the same time. Very weird. Okay, so we're going to try a question now, I think. Okay, so by the way, all these things are, if you can use the equations, even if they ask for a general equation, you can substitute and form the equations. Of course, memorizing it will save you some time, so you decide what is your bandwidth. I prefer to leave some bandwidth in my mind for analyzing stuff and memorizing chemistry. Physics no need to memorize. Anyway, you have a ball horizontally thrown from top of the building, and we are taking a random point P in mid-air, not on the ground. Okay, so now air resistance is negligible, and then at point P, the velocity, the ball is moving at an angle of 60 degrees to the horizontal. Okay, so it's 60 degree to the horizontal. So I'm going to try to draw V a bit limitedly, and then I will resolve V into horizontal and vertical. Okay, again, because the angle keep changing, the angle will go like this. It will keep changing. So I need to resolve into X and Y. Okay, so using an alternate angle, 60 degree will be there. Make sure you know how to find the angles. Okay, and then this one will be V. Again, if you don't know how to find the angle, you can just DM me. I'll arrange a time to call you. Okay, so horizontal component will be V cos 60 because 60 is beside that angle. Vertical is V sin 60. For the love of God, do not memorize vertical must always be sine and horizontal must always be cos. I'm not setting the paper, but angle is arbitrary one. I can give you any other angle. But yes, commonly they will give you the horizontal, in which horizontal then will be cos, because cos is beside the horizontal. So after this, we can now, they ask you to show the vertical component is 14.2 meter per second. So you might be thinking, walao, I don't know where the value of V is there. And if I want a Stuva, I don't have. But what I do know is that the horizontal velocity is always the same because there's no horizontal acceleration. So we like to test all these kind of conceptual ideas. Okay, so your Vx, which will be equal to V cos 60, which is always equal to the horizontal speed of 8.2. So you can equate this to 8.2. And you can find V already. Okay, if you're wondering why the text is like this, it's because I don't know, it starts to lag. Okay, so this one is 8.2. Plug it in. By the way, right, if V cos 60 is 8.2 and you can find V, you can naturally find V sin 60 already. So let's do it the old style way lah. Let's not think too much maths right now. You get 16.4 for V. And then you can find Vy. Because for the vertical component, after you resolve, the vertical velocity, Vy, will be equal to V sin 60. So I will just substitute 16.4 sin 60. Now get 14.2. Even if you can't get 14.2 in the bottom part of the question, you can still use the 14.2. Don't worry about it. Okay? That's the reason why they give you the answer, so that you don't leave the whole question blank. Alright, moving on. We are now going to determine the vertical distance in which the ball has fallen. So vertically, how far has the ball dropped? As you can see, I have changed the OneNote app thanks to the lagging. I cannot deal. Okay, so the first order of business is to list down your Stuva. You can choose not to do this if you are already very adept and very used to doing this in your head, i.e. you're already my level lah. You'll get there. Most of my students eventually get there with enough practice. But generally when I teach, I do show it because it helps people organize their ideas. Too many things now. Okay, so we have the horizontal X and the vertical Y. I'm gonna STUVA this ish. Alright, so horizontally, no acceleration. Vertically is negative G, as mentioned before. So we're going to take point P as your endpoint. So horizontally, it would have traveled X, and vertically, it would have traveled H. Now, if I take downward as negative and upward as positive. So H and G should have the same sign because the ball is at a lower position, so negative. Anyway, horizontal would be 8.2. I'm not sure. Oh yeah, and then the initial speed has no vertical initial speed, so that's 0. Okay, horizontal speed is always the same, so it's always 8.2. But I know that the vertical speed is 14.2 ma. They say one ma at point P. I just don't have the time. So without T, I'm going to choose the equation with no T. So I'll use V squared is U squared plus 2AS. The last two equations in my list previously will be given. So V squared is U squared plus 2AS will be given. S is UT plus half AT squared will be given. The first two will not be given lah. Area and gradient lah. Anyway, we're going to substitute now. By the way, V is also negative 14.2 because V sine 60 is directed downwards. Okay, so negative 14.2. U is 0. Starting point, the ball only has a horizontal component. A is negative G, and S here is your vertical height that you have 4 that you're looking for. So if you press your calculator, since I didn't assign the negative sign to H, I will expect that H should be a negative number to show that it is below the original position. Okay, so I'll get negative 0.723 meter. Okay. So generally, this is what I mean about sign. You should be very clear and not afraid about the sign that you get or the sign that you don't get. So if I put a negative H here, it means I already accounted for the direction and I'll get a positive number. All right. Determine the horizontal distance x. Now to find x, I need to find t. Again, this came from experience. And the reason why I say I need to find t is because the value of s and uv is, the value of u or v is not enough. You could say, never mind lah, I just choose the equation with no t. Like v is u squared plus 2as, can or not? Can, but a is 0 ma. So you get v squared is u squared plus 0. So you get v squared equal to u squared. So helpful. I already know what 8.2 squared is equal to 8.2. Lols. Okay, so you could say, okay lah, never mind, let's find t, but let's use this simpler equation. V is u plus at, another GG law, because a is 0. So v equal to u, L or L. Cannot. So you kind of like need to use this equation. S is ut plus half at squared. Generally, for the horizontal component, this is the one that you use. But you see, we got the problem, we need the t. Okay? I mean, a is 0, so this whole thing becomes 0. And this equation is very familiar, right? Okay, so let's find t first. Sometimes you need to use both horizontal and vertical component. So let's say I use v equal to u plus at, but for the vertical component, label wrongly, please change the x component to y component. Okay, so as you can see, I'm putting in all the y component values there. All right, so generally you can use time, not generally, you definitely can share the time between both x and y components because you only have one ball. Okay, so you have the time 1.45 seconds, and now you can put s is ut plus half at squared. Okay, I label the components wrongly. Okay, so the first one to find time was y component. The second one to find x is x component, obviously. So let's find your Vx, which is 8.2. This is why we build the table, so we don't accidentally put a wrong speed inside, like, I don't know, 16.4. Okay, so now you have 8.2 times 1.45. Okay, generally this kind of final answer, I would suggest you keep to 2 to 3 significant figure. I have a habit of keeping it to 3. Okay, part B. The part of the ball in A is drawn for you. Sketch the new part of the ball if let's say now we have greater horizontal speed, so if greater horizontal speed, that means it will travel further. Okay, and label this part G. Because it won't affect how long it takes to hit the ground. It will just affect how far it goes. So you're going to try to draw a ball that travels further, but because it's 2 marks, how it hits the ground matters. So it needs to hit a ground at an angle that is less steep than the dotted line. So this is me struggling to draw. I miss drawing on the whiteboard, miss drawing on paper. I mean, I guess I can still draw on paper, but mainly I miss the whiteboard. So as you can see, I'm doodling or trying to draw a proper parabola. Very hard to see. Okay, so as I try to draw something, and it will take some time because I don't have time to properly edit the video, I would just like to remind you, there we go, that if it's 2 marks, there are two properties that we're looking for. So in the other case, right, you have non-negligible air resistance, okay? So it will travel less far, smaller range. Because if there's air resistance, you can't travel that far. You will slow down with time. So it will hit at a more acute angle or a steeper angle. So the angle is 1 mark, the range is the other mark. But right now, I'm going to take some time to draw a bunch of graphs with you. And the reason why we would draw a bunch of graphs is I will expect definitely a kinematic question that involves graphing, either in your paper 1 or paper 2. Very important, ma. So the whole idea of this chapter 3, right, is that we have something that is moving and it can move faster and faster. It can move slower and slower. It can slow down, it can stop, it can change direction. I would like to know, how do I describe it, which I've done just now, predict it, and graph it. Okay? So when I say describe, you have to think about describing as in terms of magnitude, is it increasing, decreasing, or constant? You also have to think about it in terms of rate. Is it increasing uniformly? Is it decreasing uniformly? Or is it increasing at an increasing rate, meaning the graph is going like this, steeper and steeper, or increasing at a decreasing rate, meaning the graph is going like this? Start off very fast and then eventually flatten out. Or increase at a constant rate, like this straight line. So we don't know. Need to see. Read the question. So talk about the magnitude. Is it changing? If so, at what rate? Second point, you should always talk about the direction if there is vector. Is the direction the same? Is the direction changing? Did it change direction? Are they the same direction? For physics, only got 3 words. One lah, increase, decrease, constant. For direction, only got 2 words. Same direction, opposite direction. If you're wondering what I'm doodling about, I'm just putting up some axes so you can draw some graphs. And because there's x and y component, I am going to need to have a pair of axes so that I can draw for both the x and the y component as well. Okay? Now, and eventually just want to mess you up a bit and draw some x on the x-axis. So for kinematics, right, the common graphs will be to have time on the horizontal axis, but sometimes we can have x or displacement on the x-axis. Okay? Don't be afraid of graphs. They are the best. You draw one line, you get 2 marks. Beautiful. Provided you know what to draw now. Practice. Go do past years. Come ask me questions. Alright, I think we're ready. Are we ready? Pass me. Are you done? Okay, wonderful. So I think I'm going to label the axis now. So this is SX. So normally I like to draw them on top of each other so we can see the alignment. Okay, so S, V, and A for both X and Y components. Okay, and then it's against time. The reason why I kept negative for the vertical component is because the ball is always down. below going down, so it's always negative. Now the easiest one to write for Stuva is A. The easiest one to draw is also A. Because AX is 0, say I think 4-5 times already in this question, and AY is negative 9.81. Okay, so if your acceleration is 0, it means that your gradient is 0. Your Vx is constant, no? Beautiful. Constant at 8.2, always 8.2. So you draw one line and you label one value, and then you get like 2 marks. Wonderful. So we want to stop the graph at point P, okay? So point P is 1.45. You need 1.45 seconds to reach there. So if it's a constant velocity, then the gradient of your S should be constant. It should be a straight line. So this is X lah, the value of X, okay, or Sx. And it would have traveled a horizontal distance of 11.9 meters. Okay, so let's think about Sy, Vy, and Ay. So tackle Vy first lah. You expect it to travel faster and faster, right? So it should be increasing at an increasing rate. No lah. It's just increasing at a constant rate. The constant rate here being 9.81 for every second. Okay, so it's negative, but it's traveling faster and faster. In fact, if you take 14.2 divided by 1.44, you get 9.81. But the displacement will be steeper and steeper because the value of V is getting bigger and bigger. So the gradient is bigger and bigger, and the curve will be steeper and steeper. Or you cover more distance in the same amount of time. Common sense. Wonderful. Do not memorize, Things can go south very fast if you memorize. You should know this by now. Anyway, let's think about kinetic energy against time. I would expect, since there's a V square there, if the V is linear, then square there must be a quadratic-ish shape lah. And then you might be thinking, same thing here. If I plot against X, I should get like this, right? Okay, sure. The Ke is never 0 because the initial speed is 8.2. It will just increase as it falls faster and faster. Okay, then you might be thinking about PE. I think PE can draw on the Ke graph lah. Because if the Ke graph, if the increase by 2 boxes, then the PE graph will decrease by 2 boxes. But is the Ke against position graph correct? Well, this question need to consult some equation law. So to not overcomplicate things, I'm gonna just give you a few equations or show you how I do it. For example, I think about Ke. I know Ke is half mv squared. But I know v squared is u squared plus 2ax or as. But so this means v squared and x is linear. But Ke and v squared is linear. So can I say Ke and x is linear? Make sense? Okay. It's like A is B and B is C, so A is C. Alright, anyway, so you kind of expect a straight line, okay? And if Ke increases by, I think I draw here 1.5 box, so PE would decrease by 1.5 box too. This is PE against position. PE is mgh. Of course, it's linear. It will be a straight line. So there are quite a few this kind of objective questions. Try them. I have compiled the topicals. It's in the Google Drive. Go get it. Alright, so graphing and using the equation. I just discussed one projectile question. You should go try more. And I will see you in the next video. We'll talk about drag force.